Hey everyone, back to a new awesome video, and today we're going to continue with our series about electricity and magnetism. Today we will keep exploring our DC circuits, and we'll start by combining the resistors in the way we saw in the previous part to really simplify a circuit problem. After that, we will analyze how power is used in a circuit, and then we will introduce for the first time capacitors on our problems. So let's start. Alright, imagine that you have this circuit. This is really complex as we have 1, 2, 3, 4, 5, 6 loops on it. So that would give us 5 equations, and we also have 4 intersection points, which gives us 3 more equations. That would be 8 equations. So like such a mess to solve. Almost impossible without a computer. Like you are bound to make an error if you try to solve it this way. However, we note that in this part of the system, there's only 2 resistors. So it's pretty easy to just take this part and treat it as their own, as we did in the previous video, and combine these 2 resistors into an equivalent circuit. We know that the equivalent resistance, 1 over R equivalent, would be equal to 1 over R2 plus 1 over R3. We can solve for it if we need it. Then we can simplify this circuit in the following manner. We would get this circuit, and by establishing the currents, which is pretty easy, have I1, I2, I3, and also the current directions, the circulation directions, sorry, in this and these directions, we find simple equations, first applying the first Kirchhoff law, I1 equals I2 plus I3, and then applying the second Kirchhoff law, and we find our system of 3 equations, which is much more solvable. In fact, I went so fast over this because we solved this exact problem in the multi-loop simplification part of the previous video. In physics, we're always interested about energy, as it gives you really insightful answers about how things move the way they do, and also simplifies greatly your problems. Therefore, as we have a system, it's important to analyze how its energy moves around it. Therefore, we're going to study the power that happens in each component. But firstly, we need to recall some of our definitions. In our system, a small change in potential energy, delta U, it's always going to be due to the fact that a small chunk of charge, delta Q, has gone through some potential difference, delta B. Now recall the definition of power, which is the derivative with respect to time of the energy. Basically, the rate of change of energy with respect to time. This is no other thing than the limit as delta t goes to 0 of delta U over delta t. And in here we can substitute our expression, which gives us that this is the limit as delta t goes to 0 of delta Q over delta t times delta B. In general, we're going to have that delta V doesn't depend as much on time. Even when it does change, it doesn't depend a lot. However, the delta Q does change a lot with time. Therefore, we can approximately take this delta V out of the equation, out of the limit, and take the limit as delta T goes to 0 only of this small part. So it'll be like this. And what we have in here is that this is going to give us a derivative. So we're going to have that power equals dq dt times delta B. However, this is something we've seen before. This is the current. Therefore, we conclude that the power is equal to the current times the change in voltage. Knowing that, we can find what's the power in this simple system. We see that the power of the battery is going to be equal to I epsilon. In fact, if the battery is discharging, this is going to be power that is input into the system, and if the battery is charging, this is going to be power that is taken away from the system. Similarly, we can study the resistor, and we have that the power through the resistor equals the current times the change in voltage, which we call is current times resistance. Therefore, we have current squared times R. Note that in this system, all the power that goes in has to go out. If not, the thing it's going to end up exploding. There cannot be infinite energy accumulated. Therefore, we have that the power of the battery is equal to the power of the resistor. And what we have is that this gives I epsilon equals to I squared R. And if we take out the extra factor of the current, what we find back is the second Kirchhoff law for this small circuit. We conclude that the fact that the energy that has to go in has to go out, it's related to the fact that the voltage across a loop is equal to 0. In fact, it's probably the explanation of why it is this way. Both Kirchhoff laws come from no other than the conservation of charge and the conservation of energy. Now, just conclude that this system, what takes is transforms energy that is accumulated in the battery in form of chemical energy, it transforms it into electrical energy that moves along the circuit, and then the resistor transforms that electrical energy into thermal energy. And that is how power and energy move across a simple circuit like this one. Alright, now we're ready to examine a circuit with a capacitor. Know that when this circuit closes, a capacitor is going to act pretty much like a battery. It's a battery that stores its energy in electrical form, in electrical energy. Therefore, it gets released so much quicker. And due to that fact, we cannot ignore the fact that the output of that battery changes. What we usually do is assume that batteries don't change their voltage because their life runs out so slowly. However, with capacitors, this is not the case, and then we need to consider other different effects that happen. When examining a capacitor, we need to choose randomly where to put the positive charge. If we happen to find that the charge is negative, that would be that the charge is accumulating on the other side. But it's non-relevant. It's a choice in the same way we choose the circulation direction and the current direction. And we can always rectify the signs so that all magnitudes are positive in the end. However, if we try to analyze the system, we see that we don't really know how we need to change things when we're doing each of our Kirchhoff laws through this capacitor. So we need to first examine that. First of all, we need to establish how the capacitors relate to current, because in this case, current is going to depend on time. Imagine we have a capacitor. We have that the current goes into the capacitor. Then by conservation of charge, we're going to have that I equals dq dt, q being the charge of the capacitor. However, if the current points outside of the capacitor, outside of the positive part, we are going to have that the current equals minus the change in the charge. Moreover, we are also interested on what the change of the potential is to these capacitors, depending on the circulation direction. Therefore, let's draw both cases. Here we have the two different situations that we may encounter. In the first situation, we're going from here to here. And we have that the voltage is clearly higher here, as we have positive charge, and here we have negative charge. Moreover, we recall that this charge is related to the change in potential over here by this quantity C. Therefore, we know that delta B is equal to Q over C, at least in magnitude. In this case, as we're going from higher to lower, we conclude that it has to be negative. In this other situation over here, it's the opposite. We are going from lower to higher. Therefore, the change in potential is going to be positive. Now that we have all of these tools, we are ready to apply our second Kirchhoff law on our system. Let's use this circulation. Then we're going to have that first epsilon, first element, once the switch closes, first element epsilon, then minus IR for the resistance, and minus QC as we're going from positive to negative. It's this case over here, equals to 0. And then we note that I, as we saw in here, is going to be dq dt. Therefore, this is no other thing than dq dt R minus Q over C. And we see that to solve this system, we need to solve this first order differential equation. However, we'll do that in the following video. That is all for today. I hope that you understood everything and are starting to get a sense of all the different things that we can combine and use when analyzing these circuits. Be prepared because capacitors aren't the last thing we're introducing into our circuits, and in following videos we'll be introducing also inductors and other different objects. I hope that you understood everything, and any doubts left you may ask them in the comment section, which I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!